So, let us discuss about the second part of the image transform properties, and in the previous lecture I discussed how discrete Fourier transform can be generalized, and then we will see using those generalized discrete Fourier transform we can derive also discrete cosine and discrete sine transforms for discrete sequences, and they form a complete base. So, you can get a complete reconstruction of those sequences. So, to understand that fact, let us consider a concept of symmetric or antisymmetric extension of a finite sequence. As I mentioned for the case of discrete Fourier transform also, that given a finite sequence, you can define this sequence in the zone where in the zone of undefined region as per your convenience, make that sequence having certain properties which will be useful and which will be convenient for performing transformation on those sequences, on those extended sequences. So, one such extension type of extension that is used that is used for this purpose is symmetric and antisymmetric extension. So, let us understand what is this symmetric extension and what is antisymmetric extension. Now, you can see this is an example of a symmetric extension. As you can see, this was my original sequence, and here the center of symmetry lies at the end sample of the original sequence itself, and we call this kind of symmetric extension is whole symmetric extension or whole symmetry. Given a sample 4, actually you can see that we require another additional 3 samples, and by maintaining the symmetry of the sample values, we can create the whole symmetry. In the other kind of symmetry we can create, that is called half symmetry. In this case, center lies is separated with an interval of half of the sampling period or sampling interval from the end sample. This is the point, that is the center of symmetry. So, at this towards its left we have 4 samples, towards its right also we have 4 samples. So, this is called half symmetry. And for the antisymmetry, we also similarly define whole antisymmetry. In whole antisymmetry, the center of antisymmetry lies at a sample value which is introduced. So, this value should be 0, and then next of the values should be determined by the corresponding sequence, original sequence. They should be negative of the corresponding sample value, and this is the whole antisymmetry. So, you can see the total length in this case, in this definition, it is 4 plus this is a value introduced 5, and then this is 4. So, this is 9. This is the whole antisymmetry, an example of whole antisymmetry. Similarly, we can have half antisymmetry. So, instead of introducing a 0 explicitly here, we can assume that center of antisymmetry lies in between half of the interval between these 2 samples. So, we do not require any additional introduction of 0, only the samples are inverted here, and this is called half antisymmetry extension. Now, the significance of this symmetric extension is that if I make the symmetric extension, then you can observe this function becomes even function if we consider this is the this is the sample value at the 0th index or x equal to 0, and it becomes also even function if your origin of x lies here. And similarly, here it would be odd function once again if your origin lies here, and otherwise in this case origin lies. So, now you can, as I was mentioning, that given an original sequence, actually you have converted this sequence as an even function, and further if you consider periodic extension of this function, then you can apply discrete Fourier transform on this, some discrete Fourier transform. And then what happens that since it is an even function, that transformation will require only cosine parts. So, you can have discrete cosine transform using this kind of functions, and again you can reconstruct back using that discrete cosine transform, and keep your observation window only within this interval. So, you get the original sequence back. So, in this way you can get all the original sequence by just by using only cosine transforms. Similarly, for odd functions, it is sufficient to use only sine functions, because for odd functions we have seen that Fourier transform is equivalent to application of only sine functions from the basis function set. Here also only the sine functions can be used. So, that is what using this symmetric antisymmetric extension we can have DCTs and DSTs, or discrete cosine transforms and discrete sine transforms for any finite sequence, and that is the reason why they do exist, and you find them in the textbooks and in many applications. So, for even function it is DCT, and for odd function it is DST. So, this is what I mean, there could be various kinds of discrete cosine transforms, because you have so many different varieties. You can have different types of symmetric or antisymmetric extensions at its two ends, and observe whether the sequence become even function or odd function, and also you can also use different kinds of discrete Fourier transforms from the definition of generalized discrete Fourier transforms. So, you can have different DCTs and different DSTs. So, take this example. Suppose we have a symmetric extension, a whole symmetric extension both at the both ends. In that case, we could observe that that the functional values would be symmetric around this particular value. This is the end, and this is the period that would be defined by this symmetric extension. If I extend it periodically with this one, we will get a periodic value. So, this is the original function, and using the whole symmetric extension at this end and also at this end, we can identify this is the period, that is the minimum period that is formed by this particular extension, and if the value was 4, number of sample was 4, you can see that length of the period becomes 6. So, we will observe that how it affects the corresponding cosine transforms in this case. It is possible to have a cosine transform, and if we apply simply discrete Fourier transform on this extension, we will get a type 1 even DCT whose expression is given in this form. You can see that only it is the cosine basis function is used, cosine functions is used from the basis vectors, they form the basis vectors, and you can see the period is 2n, but you observe the definition of n in this case, the value ranges from 0 to capital N, which means there are actually number of samples is more than there are n plus 1 number of samples are there. So, if the value of n plus 1 is equal to 4, so actual value of n is equal to 3 in this case. So, that is why the period is 6, right. So, this is how the type 1 even DCT is defined. There is a definition of alpha p also. This is for the normalization operations, for making it orthogonal and orthonormal. When you are performing the reconstruction, they should satisfy this property. So, you will have this particular definition. So, similarly, we can have other kinds of symmetric extensions, HS. So, at both ends we have half symmetric extension, and if this is your original samples that is of length 4, then half symmetric extension at both ends will provide you a periodic signal of even period, even function of length 8. And if I apply the alpha, that general discrete Fourier transform when alpha equal to 0 and beta equal to half, that is odd time discrete Fourier transform, then you will find it is a type 2 even DCT, and the expression can be given in this form. And here you can observe that given n samples, we are generating a period of twice n. So, you have this expression, and this is a familiar density expression what you see in the textbook, and this is mostly used in image compressions and video compressions. And if I say density, this is type 2 event density is by default that would be considered as that discrete cosine transforms. And for discrete sine transforms, similar we can have antisymmetric extensions like whole antisymmetry extension, and given 4 samples you generate a period of, you see, 9, which should be 2n plus 1. So, I will define the definition of n. Instead of starting from 1, we should 0, we should say n equal to 1 n minus 1. So, actually you are defining it with respect to n minus 1 samples, and that would give you the twice n period, and this is what is your type 1 event DST. And for type 2 event DST, similarly we have half antisymmetric extension, and there also we are applying the this corresponding discrete Fourier transform, and this is a particular transformation matrix that we will be applying there. So, you will get a type 2 event DST, and this is the expression for type 2 event DST. There will be many other DCTs and DSTs. In fact, since there are 2 ends and we can have 2 varieties of symmetry and 2 varieties of antisymmetry. So, in total there could be 16 different types of DCTs and DSTs. And type 2 event DCT, as I mentioned, that is mostly used in signal, image and video compression. So, in a matrix form we can represent particularly type 2 DCT. For an example I am showing, all these transformation can be also expressed in the general linear transformation form, discrete linear transformation form what we discussed earlier. So, an element of the matrix, that is k nth element, can be denoted in this form, and this matrix is also referred to as n point DCT matrix, which is a type 2 DCT in this case. And in this case there are certain properties which are interesting and which are exploited in various developing different algorithms using DCT coefficients. One of these properties is that each row of this transformation matrix is either symmetric, we call them even row, or antisymmetric, and this is a particular equations by which we are expressing this property. And the transformation can be expressed in terms of multiplication with the column vector, and you get the corresponding transformed DCT column vector, and its inverse is also given in this form. In this case it is an orthonormal expansion. So, you can just have the transpose operation. So, the applications of transforms, one of the application is that it can simplify the convolution operations what you perform in the functional domain, because you can see that convolution operations in the functional domain, that becomes equivalent to multiplication operations in the transform domain when you consider the Fourier transform. So, this is a particular expressions, as you can, this is a sketch by which we can understand that the relation is that if I consider a function and if the impulse response of the system is h t, then convolution of impulse response with that function is equivalent to the product of Fourier transform of this function and Fourier transform of this impulse function. This property is called convolution multiplication property of Fourier transforms. Let us consider how this property is reflected using discrete Fourier transform. In the discrete domain, the convolution operation, linear convolution operation, can be represented in this form. Instead of integrations, now we have summations, and these are shifted impulse responses, that is unit impulse responses along the corresponding functional domain at integral points. And the linear combination of all those shifted values will give you the convolutions, as you see that coefficients of those linear combination comes from the functional value itself. So, when we perform the linear convolution, the thing is that we assume both the sequence and also the impulse response they are of infinite length. but it happens we are handling with the finite sequence, and discrete Fourier transform is also is applied for a finite sequence. So, how do you know you can how do you consider these definitions? How do you we can modify this definition, because it is not necessarily the corresponding functional domain where the function is not defined in a finite sequence. It is not necessarily they have to be set to 0. If you set them to 0, it becomes equivalent to linear convolution, but you can consider some periodic extension as we did for discrete Fourier transform definition itself. So, periodic convolution of two finite sequences is defined as convolution between two finite sequences with periodic extension, same linear convolution, and it can be observed that if they have same period, that the periodic sequence also will be of same period. So, with this definition, with this property, we can define a circular convolution. So, it is sufficient if we compute the periodic convolutions for a single period only. We need not compute for the whole function in the whole functional domain itself. So, in a circular convolution, which is its, as I mentioned, it is a periodic extension, and we can compute only with the interval of from 0 to n minus 1, and if I apply this periodicity definition, then this can be broken into these two parts. That is the definition of a circular convolution. The interesting part is that convolution multiplication property for DFT, it holds for this circular convolution. So, if I consider the impulse response of a system and functional of a finite sequence, both should be of same length, take the discrete Fourier transform and take the product point wise at the corresponding corresponding coefficient wise, take the product, then you will get also the transform coefficients of the sequence, what would have been what would have been the output of this system if they are all periodic extensions. So, this is what is your is the property in the discrete Fourier transform domain. So, what about there is another kind of convolution with anti-periodic extension. Like periodic extension, we can have anti-periodic extension. In the anti-periodic extension, first we perform the this anti-periodic extension over the functional domain, that is with an antiperiod n. This is what it is defined, antiperiodic function, and if I do this antiperiodic extension, it is also a periodic function of period 2n. That is interesting. If I antiperiodic function does not mean it is not periodic, it is not aperiodic, it is actually periodic, but the periodicity is now doubled. You can check these things. You can make an antiperiodic extension, and you will see there is a periodicity of twice the in some number of samples of the original signal, original functional, original sequence. So, skew circular convolution is defined with respect to these periodic values, or we can say this antiperiodic extensions, because we will be again observing the convolved output only in the observation window of the functional observation window of the original sequence. So, a skew circular convolution is defined in this form. You take the convolutions again from the linear convolution definition itself, but you apply the properties of antiperiodic extension, then you will get this expression. So, using this circular convolution and skew circular convolution, we can find that there are different convolution multiplication properties. Those hold also in DCTs and DSTs. I will show you some of them for DCTs. For example, you take this case that you have two functions. One of them you can consider as the impulse response, say y, and both of them of same period. So, of same interval, of same length. So, if you take the type 1 DCT of this one and type 1 DCT of this one, then if I multiply, and that is not that should be multiplied by this factor, because of the definition of DCT is what we have in this lecture. Following that, this multiplication factor would be there, and then you get your result in the transform domain itself, that is a type 1 density of the circularly convolved output of these two sequences. Similarly, a type 2 density of this one and type 1 density of impulse response will give you a type 2 density of the corresponding convolved result. You should note that number of samples depend upon the corresponding type of density what you are applying, because finally they should be of same periodicity. So, in this case you will have n plus 1 samples and there are n samples, because n sample define a density of 2n period and n plus 1 samples define a type 1 density of 2n period. So, that you need to be careful while applying these particular properties. And type 3 densities have this interesting property, where actually you can find the output is this property is applied for skew circular convolution. So, whatever we have discussed in one dimensional transform, this can be easily extended for two dimensional transforms, this discussion, if I consider our basis function in two dimension has a certain particular property, which is a separability property. So, they are separable. If I can write these basis functions into this two form, that means you can write it as a product of two basis functions. They are all independently they can be computed using a particular variable. So, this is an 1D basis function, it is a product of two one dimensional basis function. So, and also if both of them are orthogonal, then you can see that this set of basis functions will be also orthogonal, and then we can reuse this one dimensional transform computation and we can express them in this form. So, you can see that in the computation we can this two dimensional this double summation can be computed by can be written in this form. So, first we are computing the transforms with respect to the x by changing the values or sequence with respect to the variation over x, and then we are considering the transform of say with respect to the value of y. We will see that how this computation is reflected in terms of matrix operation. So, you should note here, though, in this slide I have used the same abbreviation, same notations for these two functions. They could be separate. Only thing is that both of them needs to be orthogonal to keep the orthogonality property of these basis functions. So, 2D discrete transform can be easily computed by using this separability property. So, let us consider. So, the computation would be in these ways, that you can transform columns and then you can transform rows. Suppose you have a one dimensional transform matrix B and there is an input, your input is a corresponding matrix, corresponding input is given in terms of m cross n matrix, that is your data. So, if I can transform, first I can transform columns of this input data, that is the image, in this case m cross n some image block. So, I will be transforming them columns. So, we know that dimension of each column is m. So, that is why we are using the transformation matrix, corresponding transformation matrix, which deals with m dimensional vectors, which is represented in this form. And then each column is now is represented, is transformed into another m columns. So, you are doing it for n such columns. So, you will find m dimensional vectors transformed columns and there are n columns. So, this is the matrix you will get. After that, what you can do, you can now transform the rows of this matrix, which means you have to take the transpose and then perform the n cross n. Since all rows are n dimensional, so you have to use the endpoint transformation matrix here, and then you can get the final transforms of the two dimensional image of m cross n size. So, this can be expanded. This, if I expand this y 1, if I expand y 1, I can write the whole operations in this composite form. So, the whole operations can be explained, can be described in this particular form, and that gives me the two dimensional discrete form. So, this is how a two-dimensional discrete form can be represented, transform can be represented given the two-dimensional input image. We can use the corresponding transformational matrix towards its right and towards its left in this way, and we can get the corresponding transformation transformed image in the transformed domain itself. So, typical examples could be say discrete Fourier transform. We can also express these transforms using the summation operations because they are the basis functions here or basis vectors here, they are separables, they are expressed in this form, and you can see that it is a simple extension of the discrete Fourier transform what we had in the in the one dimensional case. And using property of separability, once again we can simplify this computation, and when we express in terms of matrix multiplication, we have already defined the matrix representation of the transformation matrix of DFT, and we consider this is a m cross m transformation matrix, and this is the n cross n transformation matrix. We are just denoting it by simple m, showing it as an m point transformation matrix, Fourier transformation matrix, discrete Fourier transformation matrix. So, this will give you the corresponding transformation of the image f. So, one typical example is shown here that given this image, we can perform Fourier transform, and it will give me, since it is in the complex quantity, every transform coefficient in the discrete Fourier transform is a complex element. So, it has its magnitude and phase at every point. So, you get two components of this transformation, and in this particular image you should note that if I apply Fourier transform, the values would be in the ranges of values, coefficient values would be very large, and it is very difficult to make them display. So, we have made them displayable, and also we have shifted the origin of the transformation space. So, similar way like discrete Fourier transform, we can define also discrete two-dimensional discrete cosine transform. These are same simple extensions what we had in one dimension, and in the matrix representation we have the similar representation what we discussed for when we are extending a one-dimensional transform to a two-dimensional transform. This is an example of a DCT. So, if given this input image, you have this discrete cosine transform. In this case also you have scaling of the coefficient values, and there are, as I have mentioned, there could be 16 different types of DCT and DSTs. This is just one typical example, which is type 2 event DCT that is shown here. So, I will conclude this lecture by mentioning that why do we require image transforms. As you can see, image transform, they give an alternative representation of image. Instead of representing the image in the functional domain itself, we are representing it in a different domain. It gives a different insight of structure of images. And for example, if I consider the frequency domain representations using Fourier transforms, we get low frequency and high frequency components. So, it may become useful for providing more compact representation. You can use only a few transform coefficients to get a very close approximation of the functional representation, or you can perform selective quantization of components considering their effect on our perception, and those are used in the algorithms for image compressions, even video compressions. And sometimes many processing becomes convenient when you use these transform coefficients. Like we have already discussed about filtering, there are operations like enhancement, restoration, etc., many other operations where these transforms are useful. So, with this I end my lecture on image transforms. Thank you very much for your patience and listening to my lecture.